remarks. We will later address these in the Q&A sessions. As in previous years, the sessions will be recorded so we can share the contributions with a broader audience, and the sessions will soon be put online. In the Book of Abstracts, you can find the QR codes to the previous sessions. And finally, this is a conference for and by students for emerging conservators, so please respect one another for their exceptional effort of making this event happen. Some of our speakers will be presenting to a large audience for the very first time, so please keep that in mind. So once again, welcome to this third session of ConNext 2024. For those of you unaware of the ConNext initiative, here is a short introduction. ConNext is a joint effort of the conservation training programs of the universities of Antwerp, Amsterdam, Hildesheim, Cologne, Potsdam, Lincoln, Tomar, Westdean, Delaware, and Le Cambre in Paris, all within the field of wood and furniture conservation. Education is paramount for the future of our field, and it starts with sharing your hard work, experiences, and knowledge. ConNext tries to provide a platform for this exchange. It is our mission to provide students and emerging conservator restorers with a platform where you can share your knowledge and engage with international colleagues. Before we start, I want to take this opportunity to point out the ConNext Book of Abstracts to you. The PDF can be read and downloaded by scanning the QR code on the shown slide. The book contains all abstracts of the papers and posters presented at the 5 sessions of ConNext 2024, and we will post a direct link in the chat as well. And then we will post a link to the program where you can also download the sessions from the past 3 conferences.
I'm not sure if you can hear me. Yes,
I can.
Yes. Oh, sorry. Thank you. Sorry for the confusion.
It's okay. Do you have the script open? Do you want to introduce Bill, or shall I?
It's okay. Thank you. Just to introduce myself, my name is Anna. I'm from the Wilbar Polytechnic Institute, and it's a pleasure to be here and be part of this third session of the ConNext initiative. Do I continue, Kathy? Should I introduce Bill? Okay.
Anna, if you could, that would be great. I just muted Kathy because her microphone has a lot of echo on it.
Oh,
so
okay.
My apologies, Kathy, for doing that.
Okay.
Anna, if you could continue, that would be great.
Thank you. And I'm sorry for confusion to you all. So it's my honor to introduce today first keynote lecture, Bill Way. Bill was a senior conservation scientist at the Cultural Heritage Agency of the Netherlands from 1998 until his retirement in 2022. Since then, he has been consulting on the effects of vibrations and mechanical stresses on the condition of fragile works of art and cultural heritage. He also moderates so-called Socratic dialogues on conservation ethics. Before working in the cultural heritage field, he spent more than 15 years in aerospace and industrial research and development in the areas of advanced materials, fracture mechanics, and fatigue and corrosion. He has a BSc in mechanical engineering from Princeton University and a PhD in materials from the University of Illinois, both in the United States. In keeping with our theme today, holding it together, his talk is entitled Mechanical Properties and Testing of Adhesives. Bill, thank you for being with us. The screen is yours.
Thank you very much. Let me see, share application screen, window. Okay. Yeah, thank you very much. Oh, sorry. Wrong way. Thank you very much. It's actually an honor to be asked to be a keynote speaker for what I see is now become a traditional and excellent series of talks, of symposiums in the last few years for students. What I'm going to talk about today is based on my background in mechanical engineering. I'm not an adhesives expert, but I do a lot of mechanical testing. And in the next 15 or 20 minutes, I'm going to very quickly talk about some things about holding things together. And what I like to do is, and with my engineering background, is to give you a very brief introduction to the terminology which engineers use when they talk about mechanical properties and testing. And then I'm going to go into a few things that I think you need to think about when you are testing adhesives. So the first thing I'm going to do is I'm going to show you this slide, and it's something I do when I teach mechanical properties. And I assume that most of you do not have a formal course. I do teach at the University of Amsterdam, for example. You see here a drawing of two rods. Both rods are made of exactly the same materials. The left one and the right one, they're both the same steel. They're both treated the same way. They were both made exactly the same way. The microstructure and the chemistry is exactly the same. So now I always ask you, which one is stronger, the left one or the right one? Now, I'm not going to ask you to answer that in the chat, or because I don't know how that works. But, you know, depending on how you answer, you could be right in one way or the other. Because what I'm doing, if you look at it, the people who said the right one are correct, because I would need more force to pull that rod apart. But that's a geometrical property. I mean, that's because it's bigger, but it's the same material. So it has to have the same strength. Now, that's rather confusing, but that's part of the terminology and very simple mathematics that we use in engineering about determining strength of materials. When you look at the old literature on testing of, for example, adhesives or things, you see a lot of people use kilograms for the way they load these rods. That's what they call force, but that's actually wrong. A kilogram is a mass. And if you remember your basic physics, Newton way back, Isaac Newton, way back when, discovered that force is mass times acceleration. And now we actually call the unit of force a Newton. So mass itself is not force, it's just a mass. Although it's very confusing because, of course, if you weigh yourself, you think, oh, I weigh 70 kilograms. But that's actually not a force, that's a mass. If I want to figure out how much force I actually put on Mother Earth, well, you take my mass, whatever that is, 70 kilograms, and you multiply it by the acceleration due to gravity. So if you have a 1 kilogram mass sitting on the ground, it is actually exerting 9.8 newtons of force on the Earth. Now, of course, now we've designed the force, but we still haven't figured out the paradox of why the right rod is stronger than the left rod, even though the materials are the same. Well, the reason is that in engineering terms, what we do is we normalize our result. If you look at the left rod, I had a force force one, that needed to pull that rod apart, and force 2 is much larger to pull it apart. But if I divided that by the load carrying area, in this case, the cross-section area of the two rods, F1 divided by A1 and F2 divided by A2, I'll get the same answer. And that's been proven for many, many years. And that force divided by area is what we call a stress. Now, why am I telling you all this so fast? Well, the thing is, you know, mass and force are what you, in your conservation practice, that's what are you going to come up with. You know, things have a force. You see that chair in the middle, somebody's sitting on the chair with a certain mass or a certain force or weight. But if you go to a supplier of adhesives, for example, he sees thousands of applications and different kinds of forces and masses in a year, and he can't possibly try and compare all these for you and then figure out which adhesive you need. So he will give you a materials table given in terms of stress, because that stress can be used in any application. And it's also, if you want to compare with your colleagues what they do, you also need to compare something using the same terms. So that's why I tell you about this, and that's why engineers actually talk about strength in terms of stress. And that's how you got the situation where both rods actually have the same strength. So that's a little bit of terminology. Now I'm going to segue into the application, but still with a few terms. There are different ways of loading things. Today, to save time, I'm just going to talk about what we call static loading. I assume most of you are sitting quietly in a chair, so you are statically loading your chair. There are also things like shock loading and cyclic loading. Shock loading is very fast, and cyclic loading changes constantly with time. But I'm just going to concentrate on static loading. So here's some more words. You can have, let's see, where's my, you can have tensile loads, tension, that means pulling something apart. For example, that chandelier is hanging on a rod, which is being pulled apart due to the weight of the chandelier. The wall tapestry is being held by two cables, and those are under tension. Then you can have something called compression. For example, the chair or the furniture, they are carrying their own weight, which is pressing down on the feet of the furniture. That is called compression. And then you have something called shear. Shear is sort of a side, shear is a little hard to describe in a picture, but shear, if you put your hands together and slide them across each other, that is called shear loading. Now, in the adhesive world, people just assume that most adhesives are loaded in shear. And actually, most adhesives you would never use in tension because they would probably pull apart very easily. And of course, compression, it doesn't matter, you're pushing down on it. But most of them are in shear loading. So if you ever looked at the tube of your glue or you look at the specifications that you can get on internet, you will see at somewhere they will say, so, oh, sorry, this is in Dutch. You will see somewhere they say the strength in this case is 12 newtons per millimeter squared, or we also call that 12 megapascal. This is always a shear strength, so it's not a tensile strength. It's completely something different. Now, if we look at your applications in conservation, you could sort of say, well, a lot of things are in shear loading. For example, if you look at the two furniture joints, I mean, you have to put them together by shoving one thing alongside another, so that's shear. I talked about the wall tapestry. At the top of the wall tapestry, you see the bar going all the way across. That's being held by the cables in tension, but the tapestry itself is attached to that horizontal bar using Velcro closure. Now, if you think about the loading of the Velcro closure, that's also in shear. And then this gray thing down, if you talk about the floating mounting of a photograph or a lithograph, that's using hinges. But they are also pretty much in shear. And there are many engineering standards on how to do testing of shear, which you see on the right. Now, but the thing is, if you actually look at what you are trying to test and what your object is doing, it's not really pure shear. And actually, there are very few applications, even in the engineering world, where things are in pure shear. If you look back at this floating mounting of a lithograph, the lithograph is actually being held onto a backing board using a hinge. So you could say, yeah, the hinge is actually in a shear load because the lithograph is pulling down. But if you think about it, the hinge doesn't fail all at once. It actually pulls away. And I'm going to use the word, it peels away, which is not pure shear. If you look at reversibility, for example, and you want to remove something, for example, tape from a temporary repair, or you even want to let's say you want to redo the restoration of this vase, you don't just pull the glue away, you actually peel it away, which is also not shear. So these things are a lot more complex than just shear. Now, this is very complex for those of you who know something about paintings conservation. We talk about craquelure and flaking of paints. You could also have that with wood furniture and perhaps retouch photographs. But if you look at the bottom of the bottom one, you see how painting flakes away, and people want to consolidate this with adhesives or consolidants. What you're actually doing is trying to make sure that that paint is not flaking farther away. And even if you just look at the shape of the flake, that's also partly shear, but mostly peeling. And then you get into the really complicated situations. For example, furniture restoration. Now, this is a old chair. I'm proud of this chair. It's older than I am because I inherited it from his parents, and I knew this since I was very young. If you were to sit still on this chair on the lower right, then you would see, for example, the legs are in pure compression. But of course, if you're sitting there and you start rocking on it, well, then all of those the rods in the back are going to start bending, which means the connection between the rod and the seat, you may have pushed it in there, which would be shear, but now it's failing, not only because of shear, but also because you're bending it back and forth. And if somebody was heavy in this chair and pushed themselves out, of course, then he'd be pushing the arms out. So, you've got this motion in the furniture, and that's exactly what your parents hated you about. They wanted you to stop rocking that chair, especially the fixed chair, because that's exactly what's happening with you, with the connections. Is you're doing something that the chair is not designed to do. So what's happening now? It's not just pure shear. In this case, in many cases, what's happening is that your glue or your tape or whatever is actually peeling away. So now I've been telling you about these concepts of stress and having force divided by area. Now this is one of the very complex exceptions where if you look at the top, I'm pulling the tape away, and if you look at the bottom drawing, I'm looking down on the tape. What you're actually doing is not peeling the whole tape away all at once. You're peeling it away as a line, which is a very difficult thing, even for engineers. If you look at the lower picture of my friend Kermit the Frog, who's helping us with this talk, that's a sticky tree-toed frog, and even biologists and engineers are trying to learn how that works, that he can just climb all the way up on a tree and still stick to it and let go. If you want peel testing, it's too much to talk about today, but you can look at the European standard, or I've written a paper with a student where we tried to use a simple adaptation of doing a peel test. But anyway, I'm just trying to show you this is a special case where we're not talking about force per square millimeter, we're actually talking about force per line. Okay, but the whole idea is, you've got really complex kinds of loading. So if you're going to start thinking about testing on adhesives, you have to really think about, what is my practical application? What is actually happening? And another question you have to think of is strength the actual parameter that I really need? I see a lot of papers where conservators just say, well, we tested the materials and we finally chose this one because it was the strongest. Yeah, but what does that mean? Well, there's things you have to think about. For example, we had this very complex loading. The strongest what? The strongest, which way is it going to be loaded? It's possible to calculate it, but it's very complicated to do. So you probably need to design a practical test to try and figure out which glue you need. And it may not be just strength or shear strength. Now, if you talk about these kinds of hinges where peeling is a problem, then you might have to do a peel test. But sometimes you talk about reversibility, you might not actually want the strongest material, you might want the weakest one, because otherwise you'll have trouble peeling it off. Then you have this kind of situation, consolidation. I have no idea, I've never heard of anybody done any research, even in the painting industry, on what holds a flake down. And I think anybody who does research, academic research, it's just it's just academic research. Nobody's ever going to know how much force you need to hold the flake down. But it does have to do with handling, aging, and reversibility. So strength might not be the most important thing here. And then you have these kinds of applications, for example, repairs, or even woodwork that doesn't carry any load, where strength isn't really the most important thing. It's more handling. For example, trying to restore that pot, you might actually need to think about drying and setting time. As you know, if the glue doesn't set fast enough, then you've got to hold everything together until it dries and then stick something up there. So those are sometimes more important than strength. And something else you have to think of, we talk about adhesive strength, but you really, when you do an experiment, you also actually have to look at your result and look at your specimens and sort of think about, now, what is it that I have measured? If you look at the drawing in the upper left-hand corner, you see sort of schematically two pieces of material held together by an adhesive. Now, there's several ways that this could fail. At the upper right, for example, it could fail in adhesive. Now, then you're talking literally about the adhesive strength, and that's what people call cohesive strength. On the other hand, the adhesive could let go in the interface between the adhesive and the material, which is more common. And that's why, of course, many glue suppliers, they supply you with hundreds of different types of glue, because it really depends on which material you're gluing it to. And then you have the lower right, which is actually the most dangerous if you just blindly take the strongest glue, because what's happened here is the glue is so strong that the material of the object itself failed, which means you actually, after you restored it, and if it broke again, it broke in a different place, which actually makes the damage even worse. So these are the kinds of things you have to think about when what are you measuring, and what are you talking about when you're talking about strength as a result. And to make it a little more complicated, for example, if I do a test, glue A and glue B, and I, for example, do a shear test, and these are the surfaces of the specimen I get afterwards, it could be that glue B needs less force to break than glue A. So you would think, well, glue A was stronger, but actually glue B had a lot of bubbles in it, which means that the area you're using to calculate the stress is smaller than glue A. So even though the force was smaller to pull glue B apart, the area was smaller, which means glue B might actually, in the calculation, be stronger than glue A. But the reason you would use glue B is not because of the strength, or sorry, glue A is not because of the strength, but a lot of bubbles probably means that that glue is probably harder to handle. So again, this is an issue where, yeah, do you need strength or do you need something else? So now I've just, in 15 or 20 minutes, I've just thrown a lot of information past you, which I would normally take at least 2 hours in a 2-hour lecture. So let me just summarize the few points that I want to take away from this short lecture. The first is proper terminology, and that's a weakness in the old literature, is try and use the term stress, or when you're talking about peel forces in terms of line force, so at least you can talk with everybody, and most importantly, you can understand, or the suppliers can understand you, and you can understand them. If you're doing a practical test, try to be consistent in your test method, and also try to be sure that you're actually simulating what's happening when you're considering how to design the test. What is happening with your object when it fails? Is it in shear? Is it peeling? Or is it a combination of both? And if you don't have a lot of money and time, then you have to think, oh, if it's mostly shear, maybe I don't need to do the peel test. But it's mostly peel, well, maybe I might need to make this take a little more time and a little more funding to do a peel test. So, but it's think about what the ultimate goal is of your object. As I just said, strength is not always the most important parameter, or it's not even correct. But you know, if it is, you've got to figure out what strength level is necessary. And as I said, sometimes strength level doesn't really matter because everything works. Then it has to do with handling or reversibility. And finally, based on that is once you finish your experiment, you still have to sort of look at what you got. And then you can tell, am I talking about adhesive strength or am I talking about something else? And this also has to do with reversibility, handling, and things like that. So again, strength is important, but it's not always the most important. And as a final point, I mentioned the word standards. You know, in engineering, adhesion is a very difficult, actually a very difficult problem. And so there are many, many standards for testing adhesives, and a lot of them are actually depend on the type of product. So in that sense, you're not alone in conservation, where you seem to have a lot of different applications. I just want to note, standards are not the right way to do a test. That's something conservators still think it's the right way. but standards are designed so that competitors can show consumers that they test things the same way. Now, the tests themselves are scientifically good, so they are at least a good guideline for you to design your own test. So, if you want to know more, I did publish a book on mechanical properties several years ago. I'm embarrassed that it's very expensive, so you might want to go look in your library to see if they have it. And thank you all for your attention. And if you have any questions besides in the Q&A, and I'll be here to answer questions later, you can always write me at this email address. So thank you very much.
Bill, thank you very much for your interesting presentation on the mechanical properties and testing of adhesives. I'm sure we're going to have a lot of questions. We'll do that later in the Q&A. And let's move to our first student presentation by Abby Tudor. Abby began her career as a designer and mid-career decided to change to conservation, studying at West Dean College, specializing in furniture and related objects. She's currently working in private practice, where she enjoys the variety of projects on the bench and the opportunity to further experiment with innovative treatment options, such as flexible Lascaux fills. Abby, please.
Thank you very much. Thank you for organising this wonderful student conference. It's really great to be here. So I'm excited to share, as you mentioned, Lascaux fills, an innovative flexible fill for woodwork. I would like to apologise, I don't normally sound like this. I have lost my voice. So I'm sorry if you can't quite hear me. I'll try and project. So this was my master's thesis that I did at West Dean College with Shane Rivers, Ambrose Taylor and Kate Jennings as my co-authors. It's an ongoing project with Lascaux 498 and 303 as the focus. So I'll go through a little bit about what the project was, the overview of the problem we were trying to solve, some properties of 498 and 303, and the ideal properties of a fill and the material that we as conservators use to fill certain non-structural gaps. And then I'll go through the experimentation methods that I used in the study. So this research specifically is looking at the effect of adding colorants and mixing 498 and 303 together to create certain types of fills that we might use as conservators. I was interested to see how we as conservators use a material, how we change things when we're mixing things in the workshop. And I wanted to look at what the impact of those would be on the mechanical properties using tensile and compression testing, as Bill just spoke about there. And also the specific working properties of what we want from a fill and how this basically performed against certain success criteria. And the takeaway today is that Lascaux 498 specifically does provide a really exciting treatment option for non-structural splits in wood, and I hope you can understand about that as we go through. So to give a bit of context, this is the problem that we're looking at. It's a typical split in, say, a veneer or a non-structural area of a wooden object where you're looking to fill probably for aesthetic reasons. And to go through what's going on in the split here, Rivers and her colleagues back in 2017 presented a diagram of a split to explain what the forces are doing within it. We understand that wood can expand and contract about 1 to 2% over a year due to seasonal changes in relative humidity. But that 1 to 2% change in the wood could equal 100% change in dimension in a split, as shown in this diagram. A is the split closed fully, and diagram C is showing that it's reopened again as the wood has contracted. So we probably need something that can withstand that level of movement. I don't know if that slide's coming up for everyone. Okay, there we go.
It is, Abby, so no worries.
Okay. So just to give a bit of an example against some materials that are commonly used within the workplace. Gesso, for example, is something that we often go to as a common fill material for this type of split. And the mechanical properties displayed by gesso here are shown in very, very close to the number 5 on the grid. You can see this is a stress strain curve where it's showing the amount of stress required to basically to reach failure point of a certain material. So gesso fails at about 0.2% of its strain, which is its elongation of its dimension. And the red box at the bottom of the graph there shows all the Lascaux fills that I tested and how they continue to stretch and expand beyond the 40% of the graph I've got to show here. So it just gives a little bit of contrast of what we're looking at with Lascaux. So as mentioned, Lascaux 498 and 303 are the 2 adhesives in question in the study. I've just put here the manufacturer's properties that they advertise these with, and to give an overview, they're both pH 8 to 9 acrylic binders. They're non-yellowing and they can be both applied wet or dry with heat reactivation. You can mix the two together. They do work together as well. They're both soluble in acetone, toluene, and xylene, and through my experiments also in methylated spirits as well. The key difference between the two is that Lascaux 498 has a 400% strain to failure, whereas Lascaux 303 is over 1,000% strain to failure in tension testing. However, Lascaux 303 does dry with a permanent tack, which means it will be permanently sticky. So that's something to keep in mind if you ever want to use it. And what are the ideal properties of a fill? So in 1988, a few years ago now, Grattan and Barkley presented a survey of what conservators believe are the most important things they need from a fill. And their key properties were elastic, strong, benign, easily workable and easily paintable, strongly adhesive, and removable. And when I did a survey of current conservators today and what they were looking for, it showed that really this hasn't changed much. I think the key difference is that my survey was specific to non-structural splits. So strength in terms of the structural strength of the fill was not as important, but elasticity was definitely more important there. And the key one that everyone 28%, sorry, of the survey mentioned was that it was easy to work with. In terms of mechanical properties, Rivers again and her colleagues state that it's important for a fill to have a lower modulus, a higher strain to failure, and a lower yield point than the surrounding material that fill material is going into. So to put that into context, so what that means, we want, in terms of mechanical properties, we want the fill to be flexible. So as I spoke about earlier, it needs to at least withstand movement of up to 100% in terms of dimensional change. That's 100% strain. And it also needs to have a higher strain to failure than surrounding wood, so as not to damage that wood if that movement occurs. A lower compressive modulus, so that if the wood expands, the fill is compressed and does not again damage the surrounding wood and cause those cell structures, so the surrounding cells, to crush. So in order to evaluate that, I took two typical hardwood and typical softwood and looked at their mechanical properties, and then aimed to plot the mechanical properties of the fills I was testing against those to make sure that they sit within those criteria, and created what I called a safe zone for the fills. And you can see that here in green in the graph below. So this slide is just showing the materials used for the testing. The mixing method I kept very simple, again within mind that I wanted this to be very relatable for conservators in the workshops. So just using a spatula and sifted chalk and sifted pigment as well when I added pigment into the fills in question. And I laid out the samples as shown in these molds and then cut them to size for both tension testing and compression testing as well. I selected 10 different samples. Again, this was out of looking for what we might do in the workplace. So we like to color fills. I mean, things want to look like the background of the wood we're filling. So I did different amounts of chalk to pigment ratios within the Lascaux fills, and I also looked at other ways of dyeing the color as well, which was using leather dye and a water dye as well. The 40% chalk ratio came from a previous bit of work done at Imperial College London by Junsun Huang, who tested all the different mechanical properties of different bulking agents mixed with Lascaux 498 and their impacts on the mechanical properties there, using also SEM technology to look at the quality of the fill material produced. And his recommendation was to use a 40% chalk ratio to Lascaux. I've put here a equation which would be a really useful way of checking in basically what your wet Lascaux weight is and then how much in grams of the chalk or the pigment that you want to use. So this just shows the tension and compression setup that I used, again at Imperial College London, so that the tests were comparable with Junsun Huang's work as well. I did have a short video in this slide just to show how much that elongated, but you can see the photo on the left of the slide here, the tensile testing, that's at the point of failure, and that sample has been tested, stretched from 5 millimeters to roughly 68 millimeters, so it's about a 600% elongation till break. And then onto the working properties. So again, I wanted to look at the what easy to work with really meant in context as conservators and what we would be doing in practice. So I break it out into 5 categories. So it's ease of application. How was it to apply to the piece we're working on? Its sanding ability, its ability to be carved. It's sliced with a sharp blade when you're shaping a surface. Its resolubility, so therefore its reversibility. And its retouching ability, so does it take paints well or shellac with pigment and other things that we might use in the workplace. And then the next challenge was really to work out a way that this could be presented easily and understandably to a wide audience of conservators and how they might relate to my findings. It's a very subjective area. So I came up with an ordinal scale for each criteria, with 1 to 6, 1 being poor performance and 6 being good performance. And then in each criteria, I have basically a key of what those numbers mean. So for example, in sanding, 1, poor performance would be unable to sand. So if the surface is too sticky or too hard or whatever it might be, it's impossible to sand to the way that we like. And then 6, in comparison, it sands very well. It gives a very smooth finish. And it's similar to gesso, for example, as a reference material. And that theme with reference materials continued on with the materials I chose for this part of the testing. I chose 4 of the Lascaux samples that I tested in mechanical testing, and I also used 3 common materials that came back from the survey that I carried out with conservators. The gesso and epoxy West Systems, which is a well-known epoxy material that was bulked with 410, also from West Systems, and then B72 bulked with both chalk and glass microballoons. And here are some photos of just how this was set up. So I made some testing boards, laid out the different materials in the same thicknesses and carried out the same tests on each one. This is the process of what this looks like. So in application, I was really looking at how the material applied to the surface of those boards, and I graded them against how they felt. For sanding, I took them through 3 grades of sandpapers, 180, 240, and 320, as we would in finishing wood, and looked at how efficient they were to sand, how much dust was created, did you need to wear PPE and things like that. For carving, I used a molding test board and used 2 carving chisels, a gouge and a flat chisel, and just worked out how they felt against epoxy, which is the good reference material for good carving. Resolubility, I used 4 solvents that were quite common in the workplace. That's water, IMS, acetone, and xylene. And I timed how long these worked on each material to remove a 10mm by 10mm patch, and recorded those findings, and then graded the materials accordingly. And then for retouching, I used 3 retouching methods. One was Gamben colors, one was watercolors, and the third was the shellac with pigment. And I used the same process on each material again. And this photo just shows the Lascaux 498 with chalk on the left versus a gesso that's been painted with the same colors and the same techniques on the right. So for the mechanical property results, the stress strain curves shown here, the one on the left is with the pigments added, and it shows that the more pigment added did impact the mechanical properties a little bit, but when you're looking at the scale of this graph, all these are stretching to over 600% in terms of elongation to break. So really it's not a huge impact on the mechanical performance that we're looking for within wood. And then when we were looking at the mixing of 498 and 303, this went up to 3,500%. So it's extremely flexible with the addition of Lascaux 303. The 2 graphs at the bottom just show how all the stress strain curves fit within the safe zones that I mentioned earlier against those 2 typical woods, one oak as a hardwood and pine as the softwood. So that means that all these samples would be safe to use within a wooden split based on those 2 woods as an example. And then the working properties results, I have just put here the overall graph at the end. So the scales that I used, I mentioned I rated every material that I worked on from 1 to 6. And I've highlighted in this table the best performing ones in each category. I hope it's clear to understand. So basically the samples are down the left, how they performed in each category, and their rating is in each column, and then at the end I've given a total rating. It's just to show, I highlighted the best performance just to show that it's not always the case that Lascaux 498 performed top in every single category. It did perform well in sanding, it did perform well in retouching, but overall it performed the best. So the total rating of 24 for the Lascaux 498 with 40% chalk and pigment mixed in a 1-to-1 ratio outperformed the others in terms of my working test that I'd carried out. So that is the results. In summary, and looking at future research as well, this study did clearly indicate that it's a promising material to use, and I've used it in practice. It's good to work with. Hopefully, the things I've worked on will not need future refilling, as the fills should not crack and they shouldn't become displaced. In theory, the future work will look at that. Looking into the aging of these fills, looking at that longevity, and could be looking at cyclic loading, for example, or some forms of how this material reacts to the fluctuating relative humidity. And also something that's come up in previous questions is looking at the adhesive strength of the Lascaux against the wood and whether it is stronger than the force required to stretch the Lascaux, as that's an important factor of this study. So thank you all for listening. These are my references, and I look forward to any questions you have in the break.
Thank you. Thank you, Abby. Our next presenter is Jakob Becker. Jakob is a sixth semester student enrolled at the Cologne Institute of Conservation Sciences within the Department of Conservation, Restoration of Wood and Modern Materials. Prior to commencing his studies, he completed vocational training as a carpenter. Upon a visit to the Thone company in Frankenberg, Hessen, Jakob gained insight into the living tradition of a design classic. He was fascinated to observe how the famous Thone chair, a technical innovation of bending laminated woods, led to a unique design that became a global style icon during the 19th century. His academic focus lies in the realm of modern furniture, with a specific exploration of the intricate relationship between industrial processing techniques and the utilization of novel materials. Jakob has completed an internship at the restoration company ConNext with restorer Norbert Groth near Bielefeld. Apologies for my mispronunciation. And so please welcome Jakob.
Yeah, thank you a lot for the introduction. Good evening and welcome to my presentation. In this session, we will look at a specific case from the field of furniture restoration and conservation, dealing with the use of a non-reversible industrial adhesive in a conservation context. Yeah, what is it about? It's about a folding chair, the Rex launch chair, developed by Nico Kralch in 1956, combines comfort, style, and practical in a folding chair. The backrest and seat are made of bent plywood, which is perforated to give it a light and airy appearance, as you can see here at the two pictures. The name Rex is based on the designer's surname and was intended to attract attention at the time of upswing. Jasna Horatin describes this Rex as a symbol of success industrial design that has established itself internationally. Its industrial success and versatility makes it a design classic across different social classes. The Rex launch chair is a foldable piece of seating furniture consisting of a seat, as you can see here at this picture on the left side, a backrest, two armrests, and a frame. Its appearance is characterized by curved and round organic shapes, which are supported by a robust but light-looking frame. Thanks to its curved shape, the seat and backrest adapt to the human anatomy and the three-dimensional molded in two directions. So maybe you can see it here on the left picture again, that the moldings are not only in the middle part, so it's like molded in horizontal and in the other direction too. So because of that, there's a lot of force on the veneer layers. 11 diagonal slits on both molded parts give the armchair its light, weight, and airy appearance. To fold the armchair, you have to push the seat towards the backrest so that the two surfaces face each other. The lugs and armrest folded towards the backrest. This process made possible by a hinge plate located between the backrest and seat and a pin that runs into vertical groove in the two rear clads. Maybe you can see it here on the right picture in the middle part where the backrest and the seating are connecting to each other. There's this little hinge which allows this turning point. On the surface, there is a varnish containing cellulose nitrate, which contains alkyd resin. The varnish, it's really like aging right now. You can see it on the pictures very well. So it's not like a nice smooth surface. So it's really like brittle and a little bit hard to handle the object because of that aging surface. So the Rex launch chair is privately owned. The owner acquired the item in 2021 via the online platform eBay Kleinanzeigen. The previous owner stated that the armchair had been stored outdoors for a long period of time. As a result, the armchair was made available to the Cologne Institute of Conservation Science as a part of theoretical and practical work, as well as conservation and restoration measures. The armchair was to be returned to its practical value as a folding armchair. Mr. Fischer, so the owner, also owns other chair models from the Rex series, some of which show similar signs of damage, which I will explain later on. The concept of the restoration can therefore also be applied to other chairs from the Rex series. I'm sorry, I forgot to move on the timeline, so you can see the last of the timeline. Perfect. Now I will explain a little bit. Can you see the next presentation?
We're now at slide 6.
Okay, but in my screen it's loading, but maybe you can see it already.
We can see the damage. Yes.
Okay.
A drawing.
Okay. Perfect. So I can't see it right now, but I have it in mind, so it's okay. Thank you. So the veneer layers, the backrest and seat used to be used in the launch chair are made of molded plywood, a material created by gluing several layers of veneer together. Two of the veneer layers are crossed to prevent the moving the material for working. Beech veneer was used, which is ideal for molded parts due to its toughness and flexibility. The winding of the wood appears in spirals due to the tangle cut of the trunk. The panels have no saw marks, but cracks are visible along the grain, indicating the use of the flat sliced veneer technique. The backrest and seat are made each 400 mm long and 425 mm wide, with a thickness of 7 mm, whereby the first rows are doubled to 12 mm. The armrests are made of cross-laminated layers to increase tensile strength. The frame is made of plywood, as are the 4 studs for slats and 2 bars, all sawn from the same panels. The compartments are connected using mortise and tenon joints and screws. Traces of proceedings such as drill holes and saw marks are recognizable, indicating that the armchair was mass-produced in industrial scale. So now we come to the damage part. Now I can see the fall again. Very nice. The face veneer of the molded plywood parts of the seating and backrest have clear visible cracks that extend finely in the direction of the grain over the entire surface. Maybe you can see it better on this picture here. Particularly between the central perforation and the recess of the tenons on the left hand of the veneer surface, elongated cracks of around 35 mm in length are visible. These cracks gape open at their center, while the face veneer bulges outwards to the sides and in some cases lifts up to 2 mm from the substrate. On the seat, two smaller sides, some smaller pieces of veneer are also broken out, revealing the veneer layers underneath. On the backrest, the cracks only appear in front, on the front, while on the seat they can be found on both the front and the underside. So maybe you have now a better see on the whole object and the problems. The top veneer is detached over the entire surface in the center area of the underside of the seat from row 6 to 10. The plywood layers on the clads facing the floor are also detaching from their bonds, which gaps of up to 1 mm appearing between the veneer layers. The delamination is attributed to material fatigue of the adhesive used caused by moisture, aging, and high stresses, especially when sitting. a piece of veneer has broken out of the armrest, which is classified as a trace of use due to the delamination. The material fatigue of the adhesive used can be attributed to the various factors, in particular the aging of the glue because of moisture and the effects of the weather, such as those caused by outer storage and exposure to rain and UV rays from the sun, have contributed to this. Moisture can penetrate the wood and weaken the adhesive, while UV rays can change the chemical structure of the glue and make it brittle. These influences have caused the glue to become brittle and lose its adhesive properties, ultimately leading to delamination and cracks in the plywood parts of the chair. So now you can see the whole damage problem, especially on the glued parts. So I will continue with the working process right now. I have to change maybe to this, and then I will come later on to the glue. In order to find a suitable adhesive, it has to have a number of properties. Above all, the adhesive had to be able to withstand the high tension placed on the veneer layers. The main risk was that the adhesive would penetrate the open pored veneer and leave like darker stains that could no longer be cleaned off. To avoid this glue breakdown, menthol was selected in a test as a blocking agent. The final choice of the adhesive was made after several tests on dummies. You can see it here on the picture. This is the last dummy I chose for a really good start to go on with the restoration and conservation on the object later on. For this purpose, beach veneer test panels were pressed, which should have the same layer structure as the one on the object. I used here the UV rays to check if the glue is coming through the cut top veneer, and you can see there a little darker spot on the right side, but then on the main part there's no glue coming up to the front. So this was like a quite good example. And I used for this plate the Caride line, as you can see here on the picture. The technical specification of Caride glue confirms its suitability for use in the furniture and plywood industry, as well as its high strength and storage stability. Caride glue was selected for its specific properties. It offers high strength, durability, resistance to moisture and environmental influences. In addition to the viscosity, can be easily adjusted, which enables precise application. In this case, a reversible adhesive was not appropriate, as the delamination and cracking in the plywood required a permanent fix to restore the structural integrity of the object. Caride glue was used by applying glue and pressure to press the cracks back into their bond and stability the plywood. Menthol was applied to the surface to prevent glue penetration. The menthol penetrates the cracked surface and seals it off, allowing the glue to spread in the gaps but not to be pushed outwards. A suitable clamp system was required to carry out the pressing process. Glue screws proved to be a suitable solution, as they could be used in all areas of the object and enable adjustment pressure reduction. I will show you this process on this picture. On the left side, you can see the special clamps with the green dot on it. These clamps normally were used for like clamping violins for instruments. In this case, it was like perfect to fit between the gaps. Yeah, The clamps consisting of metal threaded rod and a round wooden head with a rubber-like washer were prepared. A Hostophan film was placed as separating layer between the rubber seals and the object to prevent sticking. Carit glue powder was prepared according to mixing ratios specified by the manufacturer. Firstly, 10 grams of glue powder and then 5 grams of water were mixed together in a beaker. Then 1.5 grams of bonite hardener powder was added and mixed again. Application of the metal was melted before on a hot plate until it formed a milky white liquid. It was then applied to the surface of the areas to be glued using a fine brush. The prepared glue was applied between the cracks and gaps using the fine spatula with a rounded tip. The glue screws were placed between the perforations of the seat and the backrest. Care was taken to ensure that they were firmly attached in the appropriate places. And the excess glue was wiped off the surface with a cloth to achieve a clean result. So we're coming now to the conclusion. In general, the use of the non-reversible adhesive in conservation and restoration is an associated with risks that can be caused by the adhesive and the object. Overall, the restoration of the plywood object with BASF Carit glue powder demonstrates the successful application of a specialized measure to strengthen and preserve the historic material. Through careful selections of materials and precise execution of the steps, the delamination plywood was firmly rebonded and its structural integrity restored. The use of Carit glue proved to be extremely suitable due to its specific properties and adaptability to the requirements of the restoration process. In addition, the correct application of the safety precautions and the precise execution of the individual steps ensured a successful restoration. This measures makes it possible to preserve the object in its authentic state and ensure its longevity for further generations. I will move on to this picture because there you can see the final result. With this successful example of the restoration technique, we can emphasize the importance of a careful and informed approach of the preservation of cultural heritage. The application of expertise and the selection of suitable materials are crucial to the success of restoration work and help to preserve cultural heritage for further generations. With this conclusion, I would like to thank you for your attention and will be happy to answer any question you may have. Thank you very much.
Thank you, Jakob, for sharing your research and insights. I'm sure we have some questions for you. And now we have time for a Q&A session. And I see that we have some questions in the chat. And let's start with our keynote speaker, Bill Way. Bill, can you please unmute your microphone?
Yes, I see the two questions from Henning and from Anna.
Yes. So can I address you the first? Can I address the first question?
Yes.
It's about, you mentioned in the end a summary with 7 points. Can these 7 points be applied to different materials?
Yes, actually, the 7 points that I use are it's what any engineer would have to think about when you're doing kinds of testing. It's just the general philosophy of how you design an experiment. It's something I learned in the aircraft industry, and you have all sorts of different kinds of parts and components and loadings. And if you're trying to select materials, you have to think about how you're testing so that you're testing reality.
Okay, thank you. And a question from Henning. Considering the various required properties, do you consider traditional adhesives used in the original construction, for example, for furniture, as suitable for conservation treatments?
I have to say that would be a question for one of my Socratic dialogues. This is a very complicated question because I mean, of course, I just gave a talk on mechanical properties, but the fact of the matter is the mechanical properties may or may not be good, but you're also thinking of all the ethical questions of whether you use original materials or you use something that's chemically less aggressive. And it also depends on how long how long you want to preserve the object, whether the object's going to be used or it's just going to sit in a museum. So yeah, I can't really say yes or no because it depends a lot more than just the mechanical properties.
Okay, thank you very much, Bill. I don't know if you'd like to add something to your presentation or to the presentations that from the students.
Oh, me.
Yes.
Well, no, I didn't have a question. I did write down lower suggested for Abby.
Okay. Okay.
And it has to do with the stresses and strains. Abby, what you're using, you introduced it at the beginning. That has to do with expansion. And it's actually expansion due to humidity changes. So my suggestion is they're very hard to find because I've actually had to try to look them up myself, but you might want to look up expansion coefficients and not temperature, but relative humidity expansion coefficients. You might find it in some of the wood industry literature, and then try to calculate what kind of strains you're actually talking about. And I think your suggestion on future research in terms of fatigue is that's actually the way you need to go. And that's the way a lot of these issues with wood objects, that's actually the big problem is cyclic expansion. And so you got that part right.
Thank you for that suggestion. I saw it. Yeah, there's so many more avenues to go down with this research for sure.
Yeah.
Thank you very much, Bill, for your answers and for your suggestion. There are also some questions.
Yes, and so I will ask those. The first one from Sophie is to Abby. What is considered a benign fill?
Yes, I saw in terms of the Grattan and Barclay survey that they did. So I refer you to their work. They might explain it better than I can now, but it's basically around it's not impacting the surrounding material. So it's a neutral pH, for example, or like non-acidic, doesn't off gas, doesn't change with age to become acidic or alkaline in that regard. It's around its kind of interaction with the surrounding materials being a neutral material.
Okay. The next question is, you mentioned, this is from Anna, you mentioned 5 working properties. Have you tested the samples isolated or integrated in a wood support?
Sorry, just say that again. Sorry, repeat the question.
Sure. You mentioned 5 working properties.
Yeah.
And the question is, have you tested the samples isolated or integrated in a wood support?
Does that mean sort of like in a split in the wood? Because basically, in terms of, sorry.
No, it's okay. It's Anna's question. Perhaps she can clarify.
So sorry to interrupt. Yes, Abby, if you've tested on wood samples or just you removed them from the mock-ups and then you tested those 5 properties, or you inserted in the woods and then tested?
I didn't insert them in any splits because what I did do is I created boards. They were wooden boards that those samples were on. So in terms of whether I put them onto a wood sample, I didn't put them into splits that I had mechanically made myself. Apart from for the carving one I did it on a molding board where I made grooves within the molding to fill up to a level and then carve them back to the same level. So that's kind of replicating what you would do when you were filling a split sort of higher than the surface of the wood and then wanting to carve back down to the surface of the wood. Does that answer your question?
Thank you, Abby.
Yeah, that's good.
Thank you.
Okay, and then we have one more question. Did you consider the glass transition temperature of both Lascaux types?
Yeah, I saw this
And-
question. And in terms of did I consider it, I'm not sure what that means in reference to what am I considering it for, but the glass transition temperature is low for both. Yeah, Lascaux 498 was I think at 13, and 303 is a negative glass transition temperature, which is probably why it always dries with a permanent tack. So in this situation, a low glass transition temperature is we want a flexible rubbery material. We don't want something that's sort of more rigid and more stiff like we do in a structural fill, where you want that strength within the material. So I think the low glass transition temperature is a good thing for this, but is that what you mean by considering it? I'm not sure.
I think that sounds good. Okay, thank you so much.
Thank you very much for the question.
Thank you. And now some questions for Jakob. Could you please turn your microphone on? Thank you.
Yep.
So, question from Henning. Did you say which adhesive had been used for the original manufacture? Do you know which one it was?
Yeah, thank you, Henning, for this question. This is a big question, or it was a big question for me because I had a really big problem to detach the original glue. It was hardly possible to find any remains of the glue, and this was not mentioned in any literature in where the chair was described in. So, but I strongly assumed it was like an urea formaldehyde adhesive. So this is what I'm adjusting then later on the chair too, and I guess that because of some hidden hints from this book here. So this was like a little bit my Bible for this chair, and this was written from a Slovenian design school, and they did a lot of researches about Nico Kralj, which was a Slovenian designer, and they mentioned that in these times they often used glues like this, but it's not specific on this chair, so I can't prove it. Yeah.
Thank you. Another question from Sophie. What were the properties of this adhesive that made it particularly suitable for this job? What were its disadvantages? What were its advantages over other adhesives? The one that you used.
Thank you for this question.
And
really,
which one it was? Which adhesive did you use?
It's an urine formaldehyde glue, so it's from the company BASF, and it's called Karit lime, and it's especially made for veneer, so gluing veneers, and it's an industrial glue, so it's used in the industrial right now in the industrial context. And the biggest steps for this choice was that I can easily work with this glue, so it can be easily adjusted in viscosity when applied to wooden surfaces, and enable precise application and even distribution of adhesive, resulting in high quality joints. And of course, there were the properties of like it's often high strength, durability, and resistance to moisture and environmental influences. In addition, the viscosity can be, like I mentioned before, easily adjusted. And this was really important for me to handle the glue in the problem zones, so that I can adjust a little bit more water or a little bit more glue powder or a little bit more harder to have like a longer time to work with this glue. Because when you imagine you have like this cracked veneer and you have to go inside like tiny gaps of 1 millimeter stuff like that. And then you handle and the glue is already hardened out or something like that. That would be horrible. So I choose the glue because of this power to adjust in every situation. Yeah. I hope it explains a little bit the process. Yeah.
Yeah, I think so. Thank you. And one final question.
Yeah.
I don't know if you mentioned in your presentation, sorry if I missed, but in your abstract, you said that the chair, it was supposed to be working again, even if from time to time. So occasionally it will be in use. How does this affected your choice of materials?
It's affected it partly because I try to choose glue which has the strength to put the veneer layers into one compartment again, so that you really have one material after the restoration and conservation finished, and that you not just like put the cracked gaps back and then everything is like nice and shiny and looking good. But the strength is not there. So I really needed a material which put the whole construction with this high stressed parts, to put this again into a whole plate, into whole materials. This was big choice for the glue too. Yeah.
Yeah, it's a challenge to work on something that is still in use. Yeah.
Yeah, right.
Thank you very much, Jakob. Thank you.
You're welcome.
Yes, so thank you to Phil and Abby and Jakob, and thank you for the interesting questions. We will collect any remaining questions and forward them to our speakers so they can have a look at them later. Now we will take a 10-minute break, and so get yourself a cup of tea or beer and some cookies or chips, and we will see you back here at, in my time zone, it will be 2:32. Thank you.
Hello, so welcome back everyone. I hope you enjoyed this short break. And let's start the second part of the conference with a presentation by Caroline Shaver. Caroline is a graduate fellow in the Winterthur University of Delaware program in art conservation in the United States. She specializes in the conservation of furniture, frames, objects, and architectural woodwork. Caroline has a particular interest in the study and conservation of multi-layered surface coatings, including lacquer, gilding, paint, and varnishes, and had previous internships have taken her to the Philadelphia Museum of Art, Winterthur Museum Garden and Library, St. Louis Art Museum, Colonial and Williamsburg Foundation, Cincinnati Art Museums, and various private practices. Currently, Caroline is completing her final graduate internship at the Cleveland Museum of Art. So, Caroline, you can start your presentation, please.
Hi, can you hear me?
Yes, we can,
Yes.
Caroline. Thank you.
Okay, thank you. There, now you can see me. Okay. All right. Hi, Anna. Thank you for the introduction, and hello, everyone. My name is Caroline, and as Anna mentioned, I'm currently a third-year student. I completed this project I'm going to share today during my second year of the Winterthur University of Delaware program in art conservation. And so this set of nesting tables is from the collection at the Winterthur Museum, Garden, and Library. They were gifted to the museum in 2019 and entered the collection without any provenance information. The fine detailed decoration on the set warranted an in-depth technical examination to better understand the objects and to speculate where they might have come from. In addition to the technical examination, I was able to treat the largest table from the set, which will serve as the methodology for future treatment of the other three tables. In the rest of this presentation, I will briefly give a little context and history as to how these types of objects came to be before diving into the technical examination of the set and subsequent treatment of the largest table. So to start with a little context, the term lacquer refers to a coating made from the sap secreted from the bark of a specific family of sumac trees that are natively grown in parts of East and Southeast Asia. Traditionally, this resin is applied layer by layer, and it polymerizes when exposed to humid air, forming a hard, durable coating. This entire process can take months or even years to complete, depending on how large the object is, how many layers are applied, and how decorated the surfaces are. Lacquerware was traded domestically between Asian countries as methods of manufacture and types of design, motifs, and decoration varied by culture, region, and workshop. This trade was well established prior to the 16th century arrival of Europeans in East Asia. Then, lacquerware production underwent several changes in response to the demand of Western consumers. Artisans would cut down on the time and quality of materials in order to meet the demands of European traders. These modifications often resulted in lower quality wares, which were more prone to degradation over time. So this Chinese tissue dish, or carved rhinoceros, shown on the left, is an example of lacquerware that was likely made for domestic use. This was made by layering upwards of 25 coats of alternating brown and red pigmented lacquers. In contrast, the object on the right is a tray made specifically for export and contains only 3 layers of lacquer as analyzed by a conservator at Winterthur. So Asian export artisans adapted and combined design motifs, materials, and techniques to create unique expressions of artistic creativity to appeal to Western markets. So now known specifically as Asian export art, these items were formed into popular Western objects, such as knife boxes, sewing machines, high chests, and yet they are decorated in the Asian tradition, usually with generalized design motifs. An added layer of complexity to these objects is that with global trade, regional styles and craft traditions began to blend together. These 3 objects are perfect examples of this phenomenon. Chinese artisans used the Japanese makie decoration on the Queen Anne style chair on the left. The sewing table in the middle is an example where the culture of origin is listed as either Japan or China because the decoration is so similar to what's been found on examples from both cultures. The corner cupboard on the right was made by a French maker who repurposed Japanese lacquer panels into his design. So the demand for lacquerware was very high, and Western makers began attempting their own versions, which is referred to as Japanning. Since Western makers did not have access to the knowledge or traditional materials, These Japan surfaces were often composed of experimental mixtures of resins and oils and have tended to yellow and degrade much faster than traditional Asian lacquers. And so, returning to Winterthur's new set of nesting tables, I wanted to see if there were any comparable examples. The tables in the set are delicate in form and have characteristics of Western neoclassical furniture, including straight lines and proportions that give an appearance of delicacy and lightness. And here are just a few images of the largest table showing more detail, as every surface of the table is very intricately decorated. Winterthur's collection has two other sets of nesting tables shown in the middle and right image. The form and style of decoration on these two tables is much simpler, with flat pierced legs and minimal surface decoration on the sides. So my supervisor, Kathy, and I were only able to find two other sets of tables that were similar in form, shown here. Obviously, the set on the left is much less decorated, but the set on the right, which sold at Christie's in 2020, is extremely similar to Winterthur's in both form and style of decoration. And so I would love to find out more about these tables, and it would be really interesting to directly compare them, as the designs are almost exactly the same. So if anybody knows where they are, or knows what institution or private collector purchased them, please let me know. So now moving on to a bit of the technical examination. I worked with one of my advisors to try and answer these three main questions. What are the original materials and techniques used to make the tables? How would these findings compare to what's been found on other export lacquered objects? And could these findings support the hypothesized date and region of manufacture? So on the right is a list of all the analytical techniques I was able to use, but I won't go into detail about all of them. I'll just kind of explain the main information that we were able to find. To capture the complete stratigraphy, cross-section microscopy was extremely useful to magnify and image the paper and pigmented ground and lacquer layers. From the sample taken from the tabletop of the second largest table, I was able to see that there was a total of 7 layers, which are numbered on the screen. There was one paper fiber base layer, which would have been applied directly to the wooden substrate. There was a coarse pigmented ground layer, 3 layers of black lacquer. One is thicker that appears light brown under ultraviolet induced visible fluorescence, and then the other 2 are thinner layers that fluoresce a darker brown. And then a red pigmented layer was applied atop before flakes of gold and silver alloy, which was confirmed by EMEDS, were sprinkled on top. And so additionally, in other cross-sections from this study, there was a clear fluorescent white layer that was added on top, and I believe it was a later restoration addition, and I'll discuss that further in the treatment section. So as mentioned earlier, lacquer is made from the sap of a specific family of sumac trees that are native to parts of East and Southeast Asia. The 3 main species of tree used are Toxicodendron verniculum, which produces a lacquer called urushi, Toxicodendron succadium, which produces Lascaux, and Gluta usitata, which produces tsitsi. And so each species of tree has chemical compounds within the sap that can be quantitatively identified with pyrolysis gas chromatography mass spectrometry. And so starting in 2014, researchers at Winterthur were able to carry out an extensive survey of 40 export lacquered objects from various collections around the world using gas chromatography, among other techniques. At the time, their study was unique because they separated and analyzed each of the lacquer layers individually, rather than as a single sample as done in previous studies. If you recall the 3 layers of lacquer I found on the cross-section I showed earlier, with this strategy, I was able to carefully separate the lacquer layers to analyze the difference between the light brown fluorescent layer and the dark brown fluorescent layer. So the results of Winterthur's survey were intriguing because patterns of material choice had started to emerge. This chart shown on the right organizes the 4 color-coded combinations of lacquer that was found. And so the use of Lascaux in the top and bottom layers was the most common combination found in this survey. The second largest grouping contained a mixture of urushi and Lascaux in the uppermost layers and Lascaux only in the lower layer. So 10 objects from this group were dated to the 19th century, with 1 outlier dated to the 18th century. And with GCMS, we found that the set of nesting tables from my study is consistent with this grouping. So this next slide is a chart excerpted from Dr. Joao Petisca's 2019 doctoral dissertation, and this is all 40 objects that were analyzed in their study. It shows also additives such as oils and resins, which are commonly mixed into the lacquer and ground layers. But as more institutions are able to analyze their lacquer collections, I'm curious to see how their findings will compare and if the data will support the patterns found in Winterthur's survey. So in addition to further analysis, there are many avenues for future research which may give insight into workshop practices, trading history, and attribution. Comparison of primary sources of lacquer workshops in Cantonese and Mandarin, and having conversations with contemporary Chinese artisans and wood ID are all research topics that are rich with opportunity to widen our collective understanding of these transcultural objects. So lastly, I'm going to share a little bit about the treatment of the largest table in the set. Structurally, the table was in stable condition, meaning it could stand on its own and the joinery was held firmly in place. Most of the condition issues were around the lower structure and the feet. And in this detail image on the right, you can see quite a bit of surface decoration was already lost, revealing the wooden substrates. So a heavy buildup of dirt and grime on all surfaces obscured the decorative designs, and a darkened, uneven surface coating obscured some of the gold decoration. And so this is the coating that I speculated was most likely applied later, probably to saturate the black color of the lacquer. And so the condition concerns found on this table were the same as the other 3 tables in the set. And so as lacquer ages and it's exposed to light, it has the tendency to become dull in sheen and physically brittle. And so with fluctuations in humidity, the wooden substrates will expand and contract, while the non-permeable surface coatings stay relatively the same dimensions. And so this tension will cause the lacquer to flake up and cup away from the wood. And you can see in this raking light image how severe the cupping was on the feet. And this kind of put the surfaces more at risk for additional loss, especially with handling. So to safely flatten and secure the lacquer back to the substrate without breaking the brittle flakes, I had to humidify the lacquer before inserting a consolidant. I made a small humidification chamber with a damp blotter paper in a plastic cup that I could mask off and strategically place over the lifted flakes for roughly about an hour until the lacquer gained a little bit of flexibility and could be gently pressed down with a silicone-tipped brush. Cold fish glue was inserted beneath the flakes with a medical syringe, and I used rubber cauls and burner clamps to gently flatten and secure the flakes until the glue had set. And after a light surface cleaning, this hazy appearance on the surface kind of remained, and it's outlined in red on the left. Some of the dirt was removed with a small aqueous cleaning test shown on the right, but once the water evaporated, the surface kind of returned to that blanched appearance. And so I speculated that this phenomenon was likely caused from partial solubilization of the restoration coating that is still on the surface. And so from this test, I knew I wanted to try a cleaning solution that would minimize the amount of water delivered to the water-sensitive lacquer. And I also wanted to reduce the amount of mechanical action that was needed to rinse and remove the coating without damaging the original decoration beneath. And because the surface was already quite degraded, a lower pH cleaning solution would be preferable to prevent further blanching. And I had a virtual consultation with lacquer expert Marianne Webb, who suggested using a solution with low conductivity, as in her extensive research, she's found that lowering the conductivity has the best impact on the success of the cleaning. And so, loading. Okay, given these parameters, this treatment became the prime candidate to test out some hydrogels. Former Winterthur paintings conservator Matt Cushman has been researching and experimenting with hydrogels made from different proportions of various natural polymers to build custom gels for unique cleaning applications and conservation. These gels are made from cost-effective, accessible materials and can be pre-made in batches and dried until ready for use, which is what is shown on the image on the left. For this specific case, we decided to test a 2% 2:2:1 xanthan konjac agarose gel to better control the pore size and the amount of solution that would be delivered to the surfaces. Given the parameters I outlined earlier, I selected a cleaning solution with low conductivity and a pH of 5 with an added EDTA chelator for more efficiency. I rehydrated the gels in the 2% solution, and then I cut them to sizes that I was comfortable working with. I simply placed each gel atop the surfaces for a short amount of time before rinsing and removing the coating. A contact time of roughly a minute was sufficient to swell the coating and the embedded dirt, and then this could be easily rinsed and removed with less mechanical action from the swab. And so in the middle image, you can see the gel became quite yellowed as it swelled the coating, and the last image kind of shows the DI water rinse with a cotton swab to remove any of the remaining material. So here are some detailed images of my tests on one of the feet, and you can see that the surfaces have become much more glossy and saturated, and the intricate details of the metallic design became much clearer. To stabilize the degraded lacquer, the humidification, consolidation, and cleaning procedures were carried out over all surfaces of the feet, the lower stretcher, and the tabletop sides. Overall, the difference is subtle, but it's definitely a noticeable aesthetic improvement as the designs are much more legible. The last steps in the process were to fill areas where lacquer had been previously lost and to aesthetically reintegrate the new fills to match what material remained. And so I fill these areas with 6% polyvinyl alcohol bulked with calcium carbonate, which is white in these images. And I carefully leveled those with a metal scalpel to match the depth of the surrounding lacquer. Each of these white fills were sealed and inpainted with gambling conservation colors to match the surrounding lacquer. Since the loss was so extensive, the curator requested that only some of the solid gold lines be inpainted. The goal of this step was to make it so that a visitor's eye would not be immediately drawn to the loss and the damage, but the new repairs would be obvious upon close inspection. And so overall, I think this treatment was successful in unifying the aesthetics and stabilizing the table so it can now be put safely on display without fear of losing more of the delicate surface decoration. The treatment protocol of this table will serve as a model for the rest of the tables in the set, which will hopefully be treated in the coming years by Winterthur conservators and future students. And so I just wanted to briefly thank these people listed on the screen for advising me on the research, treatment, and preparation for this presentation. And of course, I want to thank the ConNext organizers and all of you for listening. So my contact info is listed on the screen in the middle if you have any questions. Thank you.
Thank you, Caroline. Okay, so our next and last speaker is Kirby Martino. Kirby holds an MSc in conservation from the University of Amsterdam, specialized in the treatment of wood and furniture, as well as a post-baccalaureate in conservation from the Studio Arts College International and a BFA in art history from the Maryland Institute College of Art. Her research interests include organic and archaeological objects, natural history, polychromy, and gilding. Please welcome Kirby.
Hi, everyone. I hope you can hear me well enough. Thank you so much for having me tonight. I'm really excited to be here and really excited to share some of my early research into these really exciting objects. So tonight I want to talk about my research and then the article I wrote last year titled Broken Hearts, Suitable Support for 19th Century Wax Injected Organs. And I'd specifically like to focus on the advantages of coming at these objects from the perspective of a wood and furniture conservation training. So when I selected these objects for research last year, everyone was either very enthusiastic or a little bit disgusted by the thought of hearts hanging out in the studio. And everyone wanted to know, what are they and how is this wooden furniture related? And I'd like to answer those questions and talk a little bit about my research into potential treatments and proposed methods. First, by talking about anatomical preservation as a field, the state of the art of these objects and their methods of constructions, the conservation issues that I was presented with, and finally, my research and the proposed solutions. So, natural history, conservation, and anatomical models are as old as the study of medicine itself. On the left side, I have an image of the two wax-injected hearts as they're displayed in the Museum Brolik. And to the right, I have an image of the man who constructed or preserved these hearts, William Verlick, who made these models in the early half of the 1800s. They're displayed on the top floor of the museum, also in a medical university, and they're still displayed on the original board that Verlick made for them with his handwriting still visible on the labels. Oh, will it go? Sorry, and so as you might have seen in the last image, these objects are subject to a lot of sun, a lot of heat from the skylight nearby, and they're in an area that doesn't have relative humidity or temperature controls. So the objects are made primarily of real organs. It's a heart from a camel and a moose that have been injected with colored wax in order to maintain the volume of the organ while it dries, and to also show the different ventricles and cavities of the heart. After drying, these hearts would have been coated in a varnish, which has the added benefit of making them easier and safer to handle, but also giving them an aesthetic wet shine for display. And what's so interesting about these objects, like many anatomical specimens, is that they're somewhere between didactic teaching tool and work of art that's intentionally meant to be beautiful or aesthetic. So because of the conditions that these hearts were kept in, there are significant conservation problems. As you can see, the varnish that I mentioned earlier is significantly darkened, and it obscures the color of the wax and of the organ material itself. It's also become brittle, and it flakes off onto your gloves like glitter when you try to hold or remove these objects. There's evidence of a prior pest infestation, as demonstrated in the losses you can see, particularly in the upper right-hand corner. And because of the age and the conditions, the hearts are quite brittle, and you can see that the arteries have become detached from the larger heart structure. And in the case of the image on the lower right, some of the arteries are literally holding on by a thread. So this was the issue that I became most interested in exploring in my preliminary research. I was working with the research question, what are the most workable methods by which to provide internal structural support to a 19th century wax injection zoological preparation? So I was thinking about suitability in the piece and substrate combination and application method would make it feasible to reconnect two sections of organ material or to reconnect an artery to the larger heart structure. So, as wooden furniture conservators, I think the first thought is adhesive and clamp. They're used to using clamp or weights or some straight edge to apply outside pressure to achieve a good fit and a good bond. However, with your objects are usually shaped and extremely fragile and sensitive to pressure or heat, and this is a workable solution.
Kirby, apologies for interrupting, but your connection is really bad at the moment, and the sound is really glitchy. Would it be possible to move closer to your Wi-Fi connection? Sometimes that helps. I'm sorry for interrupting and getting you out of your flow.
Yeah, no worries. No worries. I can try. I'm in an apartment where I'm not quite sure where the Wi-Fi is, but I think it's in here.
So let's just try. Better? Yeah. So please continue. Maybe turn off your video otherwise to reduce bandwidth. That might also be an option.
Sure.
And maybe if you can go back to the go back 2 slides if you don't mind. Would that be okay?
Yeah, can everyone see this slide now?
Yes, yes. And I think the sound is better now. Thank you, Kirby.
Okay, amazing.
Yes.
Great. No worries. Thank you.
Okay, thank you.
So as I was saying, or trying to say, I was most interested in addressing the issue of the detached arteries because of handling, because of fluctuations in heat, humidity, and the extreme brittleness of the organs. The arteries have become detached and are at risk of dissociation, as well as right now they're not in the state that they were intended to be seen. So my working research question was, what are the most workable methods by which to provide internal structural support to a 19th century wax injection zoological preparation? And I was interested in a suitable adhesive and substrate combination, and what sort of application method would make it possible to reconnect two sections of organ material. And as someone with a wooden furniture background, my mind immediately jumps to clamps. I think we're very used to using clamps or jigs or weights to apply pressure to flatten and to achieve a good bond using an external force. But in the case of these hearts, which are unusual organic shapes and extremely fragile, this isn't really a workable solution. So I started to think about what properties of the hearts and of this unusual shape might be helpful to coming up with an appropriate way to reattach organ material. So I've included the images of two of the arteries that have become detached. The top one, I've inserted a slip of Japanese paper in between the wax and the organ material to demonstrate that there's a gap in between the wax and organ, likely due to a difference in expansion and contraction of the two different materials. Whereas the image at the bottom shows how, in some instances, the wax is still flush against the organ skin. So a few different situations to consider when thinking about readhesion. But I came up with this diagram to start to parse out how I might work with essentially these tubes or these cylinders. And so in the top image, I've represented the wax in red and the organ material in yellow, showing how the organ material encompasses but doesn't always touch the red wax. A first potential solution was to think about applying a bandage over top of the organ materials to reunite two pieces of artery or the artery to the larger heart complex, which I wasn't excited by, both because I don't think that this would be a seamless or aesthetic repair, but also because the varnish is so darkened and so flaking, it doesn't provide a suitable, stable support to adhere any sort of thing really to, and also because I think that it's a good candidate for future conservation treatment to lighten or remove the darkened varnish. And in doing so, anything glued atop it might or would need to be removed as well. So it's not a long-term solution. So the idea that I came up with and that I was most excited about, that I used as a jumping off point for my further testing, was to take advantage of the gap in between the organ material and the wax, and to try to insert some sort of fill, some sort of substrate between those two areas. And in doing so, take advantage of the intrinsic nature of a tube or of a cylinder. If you roll up a piece of paper, it doesn't stay rolled up, it wants to expand. And so by inserting a fill that rolls into that gap, the natural expansion would apply pressure to help achieve a bond. So instead of using a clamp or a weight, the fill itself is its own source of pressure. So even though this is largely about the advantages of wooden furniture conservation in approaching a natural history object and construction, one of the disadvantages was my unfamiliarity with the adhesives and the substrates most used in natural history. So I started with a literature survey of anything to do with book and paper, with leather conservation, with taxidermy, and with the conservation of gut skin parkas to get an idea of what sort of adhesives and substrates I should be looking at. And then once I had a way too long list, I started testing each by applying each adhesive to each substrate in these squares to get a feel for how it bent, how it dried, whether it was flexible or more stiff. And then once I had a good selection, I decided to put the diagrams from the previous slide to the test, because even though the diagrams looked like they would work on paper, I was curious about how this idea of inserting a fill or a tube of paper into these organs would actually work in real life. So I included a photo at the bottom of a facsimile of the organs or of the arteries using a wooden peg as a stand-in for the wax and 2 pieces of parchment as a stand-in for the organ material. And through tests and tried to make my ideas from my diagrams a reality. And so through testing, I came to like using a 1-to-1 mixture of 10% Clucil G and Evacon R because it was an extremely sticky, grabby sort of adhesive to work with that allowed a fill to be put in place but also adjusted. And I liked working the most with Japanese paper, both 19 gram and 32 gram, because it was easy to work with and flexible. And so in these tests, I came up with 3 different methods that I think are feasible for the repair of an object, like the wax injected hearts that I'm calling the tube join method, the bridge join method, and the edge join method, which I now have photos of. So the tube join method is like it sounds, inserting a slip of pre-coated Japanese tissue into one side of the artery, taking advantage of the way paper in a tube intrinsically wants to unroll and applying that outside pressure to the organ material. And then once dry, doing the exact same thing on the second piece of artery or the larger heart. And this was a little bit tricky to get right, the kind of fine motor skills needed, but once everything was dry, it was a pretty solid, pretty dependable connection, and one that didn't involve disturbing the varnish on the outside or the wax inside. I also tested what I'm calling the bridge join method. There's the arteries, there's not a continuous gap all around the wax because of the way the wax is over time. In some instances, there's only one area of a small gap. So I've come up with a minimally invasive fill that involves a small Japanese tissue paper bridge that attaches to the interior of the organ material and a outside fill that wraps around in order to provide a visual fill, but that also, as you can see in the photo on the right, is only attached to the organ material at one point. So this will still prevent further disassociation, but also works with the the structure of the broken artery pieces. And finally, for the instances in which the wax was still flush with the organ material, I came up with a idea that involved using the feathered edge of the Japanese tissue fill and the extremely kind of grabby, sticky Klucel-Gene Evacon R mixture to only adhere a fill to that very thin, I guess the width or the kerf almost of the organ material on the artery. And this was only a small part of the entire research this was focused on construction and joining in a more physical sense, while the larger research focused also on diagnostic testing and also on historical reconstruction. But within this research, I think that there is a lot of opportunity for further research and next steps to better understand these natural history objects, but also how we can better care for them. I would really be interested in further diagnostic testing of the wax and the organ material itself, and also of the aging and degradation testing of the proposed adhesive solutions. This represents a series of first experiments into this sort of work. And as I was thinking about when I was listening to Bill's presentation, especially, I really don't know anything about what the long-term effects of mixing, for example, Klucel-G and Evacon R. I think that before this is actually applied to any cultural heritage object, this sort of testing of aging, of shear strength, of elasticity, of glass transition temperature is paramount. And then finally, I would be interested in larger applications to the object, but in this sort of natural history object in particular. But I would like to thank you for listening to my presentation and for having me. I would also like to thank everyone who made this research possible, which is more than I could fit on this screen, but particularly my supervisor, Thijs, and the Museum Vrolijk and the curators at Museum Vrolijk, Lawrence DeRoy and Lodi Brokens. And I look forward to your questions either after this presentation or if you'd like to send me an email.
Thank you, Kirby. Very, very, very interesting presentation. I'm sure you have some questions for you. So now we have a short Q&A session, the last one. And may I ask your speakers, Caroline and Kirby, to turn on their microphone when we address the question to you. And let's start with the first question for Caroline from Julia. What criteria did you use to select the glue for consolidation?
Yeah, that's a great question. So at first I was kind of thinking about if the glue would be compatible with material itself. So a lot of the lacquer grounds are kind of made with protein glue, so I kind of turned to that first. After that, I wanted to choose a glue that would flow under the flakes with enough time to then remove the squeeze out after they were clamped down. So with the hot glue, I found that there wasn't enough time for me to have all of those things happen at the same time. So I did end up choosing a cold fish glue for that reason. Yeah.
Okay, thank you. Another question now from Henning. Could you explain the procedure for charging the gel? Was the first step before charging to let them dry out internally?
Yeah, so for the gels, they don't have to dry out. You could make them fresh. For this type of gel, you can heat them in it's like an immersion circulation bath, or you can heat them in the microwave. And then once you pour them out into the shape that you want, once they cool, you can just use those straight away within the solution. But for the dry gels, I kind of just wanted to show that that is a tool that could be used, especially for like if you're going on the field or something like that. So you can dry them and then put them in your solution, and they work just as fine. So.
Oh, that's interesting. With that comment that you made about take them to the field and then just prepare it in situ. Yeah, it's an interesting approach. And I also like very much your humidification chamber.
Thank you. Yes, I thought of that myself, and I was very proud.
I really, really liked it. And did you apply that kind of chamber in all the areas, just like bit by bit?
Yeah. So I wanted that because I didn't want to like humidify areas that were flat and have those come up. I just wanted to humidify the areas that were already lifting. So I found with the little cup, I could like mask off exactly the area where I wanted the humidity to kind of like flow onto the, not flow, but affect the lacquer. Yeah, and with the cup, I was able to just like turn the table sideways and then just have it sit on top with like a little weight. So I found that to be effective.
Right. But did you use like warm water in the cotton or cold water?
No, I just used cold water on like a little damp blotter paper. And I made sure to like wring it out so it wouldn't drip onto the surface. Yeah. Mm-hmm.
Also, you applied a paper between the cup and the surface?
No, so the cup was open, but I like shoved the blotter paper inside the cup so it wouldn't drip.
Okay, I understand. Okay, I see. Very, very interesting. Very resourceful. Let me see. I don't think. No, thank you very much, Caroline. I don't know if you would like to add anything to your work. When did you restore these tables? How long ago?
This was last year. This was like one of my major projects during my second year, and I actually did this project with Kathy Gillis as my supervisor.
And they are still okay? No changes in the consolidation?
I don't know. We'll have to ask Kathy.
Okay.
They're fine. They're fine. Sorry, I keep having technical. Whoops. I keep having technical difficulties, but.
Okay. Thank you, Caroline. Thank you, Kathy.
Thank you.
Okay, so now I have to get back to my script and the and questions for Kirby.
Yeah.
So I have a question while I try. There's my script. Okay. What is the plan for the this object now that the treatment is finished?
Well, the treatment isn't actually finished. This was a 3-month research period in which I was able to come up with ideas that I'm really interested in pursuing that I think are potentially workable and even really good solutions. But I didn't have time to apply these solutions to the objects and might not feel comfortable doing so without a little bit more research and a better understanding into the aging and strength and material qualities of the adhesive that I ended up favoring. So the ideal next step would be to do this research and actually treat this object. But right now it's back at the museum, and I believe it now has a little bit more temperature and humidity control as well, which is always a plus.
Yes. Okay, thank you. I don't see any more questions in the chat, but my fellow moderators can perhaps help me if there are more questions that.
Yes, I think we have here. Have you been able to use or adapt the method you developed during your current internship? I understand that you didn't. This is just a test. Did you use it in any other experiment, Kirby?
Oh, thank you. I think that I'm about to. There's a real lack of wax injected hearts at the museum I'm currently interning at. But I will start treatment shortly on a crab. I'm currently at a natural history museum, by the way, but the crab has actually really similar problems to the heart in that it's dried out. It has this very delicate kind of, I guess it's more of like a keratin, but this proteinaceous structure, and it's essentially a lot of tubes or a lot of arteries, artery-shaped limbs attached to a crab. So I think that I actually will have an opportunity in the next few weeks to test and adapt this method, and I'll take lots of pictures. Hopefully it will go well.
Okay, nice. And you also mentioned that you didn't restore the heart, but the temperature and humidity are now more stable. But are you going to intervene to work on those objects, on those hearts eventually?
I would like to. Actually treating the hearts wasn't exactly in the plan for the research. The hearts were selected as an object for a jumping off point in terms of testing potential treatments, but I think I would like to treat the hearts, hopefully at some point.
Okay, thank you. Kathy, I don't know if you want, there's a question here from Bill. Yeah?
Yeah, I was looking at all your pictures coming across, and at the end of the day, you had something at the end about the edge joining method, and that's why I sort of lost the difference between that and I guess the bridge and the tube. I saw a bridge, I saw a tube, and I saw edge joining, and you also talked about something about rolling up. Actually, I found that one interesting. Rolling up paper and how it wants to unroll and apply pressure. I'm not sure whether maybe I just glanced away, but I didn't quite catch the. I would have been interested in how that worked.
Sure. Is there still time to?
Yeah, Kirby?
Okay.
Yeah.
Yeah, maybe you glanced away, but also maybe the audio cut out. But so in terms of the edge joining method, this is a method that I proposed to work on a portion of the piece on one of the broken arteries where there wasn't a gap in between. Oh, thank you. Where there wasn't a gap in between the wax and the organ material. So where there wasn't a gap in between the wax and the organ material. So the tube join method, the idea is to take advantage of that space between the wax and the organ material present in some of the areas on some of these breaks. I don't know if I can find the image again, but this is what I was saying about if you roll paper into a tube, it wants to unroll. I essentially inserted the slip of tissue paper into this makeshift artery, and the glue was grabby enough, sticky enough that it mostly stayed in place, but still had enough workability that the paper was able to roll or expand just enough that it pressed against the adhesive and against the interior of the artery. So it expanded to fill the space that it was put into, in the same way that if you rolled up a piece of paper and then held it loosely in your hands, it would expand to touch your palms. This is the same idea, but using the paper to exert, using the fill material to exert force on the area to be filled, or the area in which it was glued. And which is different, of course, taking advantage of that space in between the wax and the organ material versus using a feathered edged and kind of grabby, sticky adhesive to grab and only adhere to what it touches, ideally the width of the organ material.
Okay, thank you. No,
That helpful?
Yeah, you were right. It was right when it was breaking up, and now I see the image again. Now I understand it. Thank you very much.
No, thank you for your question.
So thank you very much, Kirby. I think this brings us to the end of the third ConNext session. We would like to thank again our keynote speaker, Bill Way, and a big thank you for all our speakers, Abby Tudor, Jakob Becker, Caroline Shaver, and Kirby Martino. We also like to thank our institutes and partners, and of course, thank you, the audience, for making this event happen.
Okay, the next session is presented under the title Wood and Textiles, and we will start with our keynote speaker, Heather Porter. This session will be hosted by Andreas Krupa and Marjolaine Free. So hope to see you all next Tuesday at the same time and the same place. And thank you again, everyone, for being here, and to our speakers.
Thank you.